Welcome to the lecture on linear programming. We saw in the previous classes that our feasible region is convex, our optimization function is linear. This allows us to have very nice properties for the optimization. In particular, for linear program, we can write three important things which will allow us to give an algorithm. Right? What are these three properties? Local optima implies global optima, and this happens because of two things. One is our optimization function is linear, convex as well as concave, and our feasible region is convex. That means if I take 2 points, the line joining them stays inside the feasible region. Because of this property, we can show that a local optima remains a global optima. So if I find a point in my feasible region where in every direction my value increases, I have found the minimum point over the entire global domain. Make sense? Secondly, we realized feasible region is a polytope, and this happened because one of the standard form, the constraints look like this, and we know that this is a polytope, a polygon or a bounded or an unbounded polytope. Correct? And this is because of Minkowski-Weil. Thank you to both of these guys. We are very happy that they prove it for us. And then the third property is optimum will be on the boundary. And why is this happening? Again, convexity, right? And again, we will use both these things, because if I take a point P and let's say it is a combination, it is not on boundary, that means it can be written as a convex combination of 2 points Q and R, right? Then what I can show, if I am interested, let's say, in a minimization problem, f of P would be greater than minimum of f q or f r, right? And it is easy to prove. How will you prove this? Take the contradiction. Suppose fq and fr are bigger than this. Then you take the convex combination of that, fp has to lie above this, and this works out, right? So you can check. The good thing is our objective function is linear, it is convex as well as concave. For one minimization, one thing will work, for maximization, other thing will work. So it will turn out that in all the cases, if p is the optimal, then we know one of the q and r should also definitely be optimal, right? And I can, this way I can keep going outside, right? And finally reach a vertex. That means there exists an optimum at a vertex. Okay, I am not saying all the optimal values are at vertex. Important, there at least one optimum which will be at a vertex. And this gives us the outline of simplex algorithm. Right? I will start with a vertex, check if it is an optimal vertex. Question is, can I check it? we will see. But again, this is just an idea. And this algorithm actually we will see in multiple stages. I will give an idea, formalize a part, again give more idea, then formalize, and finally we will have an algorithm. Okay. So intuition is start with a vertex. How we will check if it is optimal, we will see. But if we can check, if it is not, then there has to be an edge. Notice I am not saying direction now. I am saying an edge. Why can I say edge? But again, this might be, but why should this be an increasing direction?
If both are increasing, then it will be optimal.
No, if both are increasing, then it will be an optimal. And here, this is not a local optimum. That means it says that there is some direction here where the value increases. I am saying there is one of these two are there where the value increases, because this might be optimal, right?
Take it for a maker slash transfer.
Exactly. What you want to show is that suppose if I am increasing in this direction, then because of convexity, either in this direction I am increasing or in this direction I am increasing. If direction is confusing you, take a step of some t, draw a line, and then you can see that at least one of those will give me the increase in direction. Assume we are interested in the minimization problem, right? So it is sufficient to look at edges again because of convexity. And then if to other vertex and check if it is optimal, or I should say repeat. I haven't explained many things, but at least the idea is clear. Right? How do I start with a vertex? What do I mean by a vertex? And that will be the first question we will answer. But if we know that, what does it mean by moving to another vertex? Even if we find a direction, how far do we have to go? Right? Does it stop after a finite amount of time? Does it stop after a finite amount of time?
Number of points are finite, then yes.
Number of?
Points, vertices are finite.
Can there be a case when number of vertices are infinite? We have a polytope. If there is a cone and there is an increasing direction, then the value is unbounded. So here, if we find a direction to move and we are not reaching any vertex, then the value is unbounded. That's also fine.
Circle.
Exactly. So then you should remember, we cannot have a circle. We know that a feasible region is a polytope. That means it's a convex hull of finite number of points. Right? So it cannot be a circle. So the number of vertices are actually finite, number of directions are finite. And this, since my value keeps decreasing, it's a minimization problem, my optimal is better and better, it has to stop. So this is fine. What about efficiency? Is it efficient?
Depending how to find a vertex.
Exactly. So don't know. And this has been open at least for 70 years. And this question depends on how you are doing these things. As I said yesterday, there are multiple implementations. For most, or I think probably for all the standard implementations, there are counter examples which go over exponentially many vertices. Okay? But still, there is a possibility that there is some implementation which works in polynomial amount of time. This is an exponential time algorithm. And from whatever you have been taught in computer science, you would say, oh, why care about an exponential time algorithm? But if you look at any algorithms literature and you know the marvels or gems of 1900s, this will be one of them. The reason it's simple, it's applicable. Many industries still use it. So in practice, this is a great algorithm. And this has very simple idea, easy to implement, easy to understand. That's why this is very popular and mathematically very nice. So the first important question when you look at this kind of outline is, how can I describe a vertex? Yes, great. It looks, in my picture it is at the corner or something. It is not the convex combination. But for my feasible region, how do I interpret it in terms of my inequalities? That's the first important thing I want to figure out. Okay, that will be my handle to start this algorithm, because if I look at it, I think multiple times I repeat the word vertex appears most number of times except probably A and with or something. So we really need to figure out what vertex means for us mathematically, right? That will be our first goal. And again, you will see this interplay where now suddenly my standard linear program will be this. Okay, when you wanted to understand the feasible region, we said Ax less than equal to B. Fine, but that can also be written like this. And now we will play about look at vertices in this. Okay. But before I give you the mathematical description, there is a mathematical description. Let's try to see if we can get some intuition of what a vertex should look like. And once again, the idea would be to look at two dimensions, right? Our favorite dimension. So then, let's say I am interested in this region. Okay? Again, optimization, objective function, none of my concern. I am looking at the feasible region now. That's what I am focusing on. Oh, by the way, before I start, does anyone have a nice description of a vertex? Then we don't need to. Seems like a complicated enough problem, right? Mathematical.
The only linear combination creating it is the vertex itself.
Convex combination. But that's not a handle, right? That's not a good representation like Ax less than equal to B, you see. So you will see what I mean is.
We can say
You are getting closer, but not really yet. We are not there yet. So yes, but it is kind of a unique solution. But why n equations and n variables?
if there are n minus 1 equations, then we won't, like the solution would not be a vertex.
So you want to have n equations from here?
Yeah, n or greater than.
So I can assure you, okay, if for equal to n or greater than equal to n equations, this is a useless program. Because this is equality, I only need to put linearly independent number many of equations. If an equation can be written in terms of other equations, if the constant follows the same behavior, then that equation is useless. If the constant doesn't follow the same behavior, it's infeasible. Is this simple point clear? That I only need to worry about linearly independent equations here. Right? And if the number of linearly independent equations are n, then this has a unique solution. This is nothing. And I just have one x. I can figure that out using Gaussian elimination or something, put it and get the answer. So the interesting case is, so I would assume that if there are m equations, m is less than. Now, what do you think is a vertex? you are still, though you are close. Okay, so now you are guessing. That's okay. So let's see. Let's try to guess, but in a more, informative way, right? So let's try what happens, right? This is the graph. What is my feasible region? Correct. Now, these are the vertices, right? And then what is happening at the vertex? Many of the coordinates are becoming 0. This is because we have changed this to equality, and this is greater than or equal to 0. So basically, this is a linear subspace which is going to cut into orthents. So then your vertices will have, a certain number of zeros. And you see it here. But how many zeros? What are they? That we have to still figure out, right? So, and the other point is, if I have lot of zeros, that's a nice way to get a vertex. Because if this is a linear combination of 2 points Q and R, then what do I know? That these coordinates are 0 in both Q as well as R. Once more, if P is a linear combination of Q and R, and let's say P is 0 in last K coordinates, my claim is in Q and in R, last K coordinates have to be 0. Because P is a convex combination of Q and R. All these have to be positive. I have this constraint. If I take convex combination of this coordinate and this coordinate, it is still going to remain positive. So this has to be 0. This has to be 0. These have to be 0. Agreed? Right? So to get a convex combination of P, get P as a convex combination, and there are a lot of zeros, this is pretty hard. Right? So you can see it in multiple ways. Linear subspace cutting these axes. In this way, you should have your vertices should have a lot of zeros. That's the idea. Right? So let's look at A, and let's say x is 0 at some coordinates, right? Okay, so let's say last K coordinates, some point, let's call it P. Okay, x is a variable. Let's take a point P which is 0 at last K coordinates. Okay, now I look at the first n minus k coordinates, and I can restrict A to first n minus k coordinates.
What is A again?
A is your constraint matrix. This is the linear program. This is the feasible region we want to target. We want to understand the vertex of this set, this polygon. Right? Is this clear? Okay. Now you know that A times P equal to B, but last K coordinates are 0. That means A n minus k times P, let's say I restrict it to first n minus k coordinates, right? And suppose this is invertible. Your idea, okay? And probably you might have had this intuition at some point, but now if this a n minus k was invertible, that means this is unique, and that means this is a vertex. Think about it. You have p n minus k, you have zeros, you have q and r. What did we realize? This has to be 0 and this has to be 0. But then q and r are also feasible solutions. Correct? That means a n minus k q should be equal to b. A n minus k r should be equal to. But that's a problem. I can't have 3 different solutions for this invertible A equation. It has a unique solution, right? Again, this is just, and I'm going to give you the mathematical description, but the idea which is going on behind this is, oh, there has to be a lot of zeros, and once I look at zeros, I look at the remaining columns of A. If they're invertible, job done. With this intuition, now let's define a vertex. Actually, I will not define a vertex, I will define what is called a BFS. And then we will show that a basic feasible solution is a vertex is a basic feasible solution. Okay? So, what is a basic feasible solution? It is described by a subset. Remember, I had n variables, and this subset is going to be n minus k. Right? I had written it as k coordinates, but these zeros could lie anywhere. Okay? So, this set will be called the set of basic variables. Xi is such that I element of S. And I will have non-basic variables, which is n minus S, let's note them by n. Okay? And then what do I need? 1. So, xi equal to 0 if I is basic, right? This is how I started with. This is the set of zeros. The non-basics are the set of zeros, remaining part was the set of basic variables. And part 2, if I restrict A to S, this is invertible. So, what is happening here? AS XS plus AN XN is equal to B, right? This is just AX equal to B. This is matrix multiplication. No. This is a column, right? So this is a linear combination of these columns. So this is S, this is N, right? So this dimension matches this, but the length, right? So think of it as this is a linear combination of columns of A from basic set, same dimension, right? So this we are still working in the column space of A. This is linear combination of non-basic columns. Basic columns, non-basic columns. Will you be happy if I change S to B or keep it as S? right? And now what do we know? Xn is 0, right? That means Xs is the unique solution for ASXS, right? What it means is that if I fix my S, correct, then I get XS. So my basic feasible solution is described by S. Can you tell me what is the size of S? And we have assumed that every row in A is linearly independent, right? Exactly, because row rank equal to, exactly, yes. So cardinality of S is number of rows in A, or M. Yes, you are right. What is the problem with that? You seem confused. This is what you want to show, yes. So you see, right? All my rows are linearly independent. That means the rank of the matrix is M. So if I want to make it invertible, the size of S should be equal to M. Other words, a basic feasible solution is described by a subset of N of size M. You fix a subset, create everything else outside 0, then remaining things, they should be invertible. If they are invertible, then only it will be a basic feasible solution. Otherwise, you forget about it. If it is invertible, you solve this equation, this gives you the value of the remaining variables. You have everything. Okay? So you see a good reason to define this kind of a nice solution from here, right?